Going over what we started last class, we have two different theories of bonding. And these work together and they work separately. They're just different ways of explaining how bonding works. And each one has their own benefits. So the first one that we'll end up talking about is valence bond theory or hybridization, where in this situation, each atom is going to have its own orbitals. Now remember orbitals that we've been talking about being S, P, D, F, and G, and so on. Well, it's going to keep its own orbitals, but now it's going to take the ones that have that are going to play roles in bonding, and it's going to rearrange them a little bit. And it's going to take all those orbitals we've been talking about and make a bunch of new ones. But each atom is going to keep its own orbitals. And then the orbitals from different atoms are going to overlap each other, and that's what's going to form your bonds. MO theory is very different from that. What's happening in MO theory is you're taking an orbital from one atom and an orbital from another atom, and you're combining those together, and that's what's going to form your bonds, okay? So two different ways of looking at it, each one with its own benefits. So first we're going to kind of go into what bonding is and what bond lengths are in a little bit more detail. So this is an image from the Chang book that we used to use, but there's similar ones in your book. So this would be an example of something like hydrogen bonding. So two H's bonding. So you would have one hydrogen here, and the idea in this simplest form of bonding is that you have these s orbitals, and that in order to form a bond, they're going to have to overlap, and they're going to form this bonding situation where they can share the electrons, okay? You have this sharing of electrons going on. Now, we've sort of mentioned off and on bond length and talked about it a little bit, but not in detail. Well, the reason why there's going to be a particular distance between this distance and this distance is that when they're far away, they aren't really sharing the electrons that much, and so they aren't in a stable electron configuration. So as you get closer and closer, they're able to share the electrons, and they form that bond. If they get too close, and the nuclei get too close to each other, that causes a problem, and then that's not going to be stable either. So what this sort of diagram is, and it's a good diagram to get used to looking at, especially if you're moving on in chemistry, you'll see them a lot, is you have potential energy here, and you have distance here, so the distance between the two nuclei. And when they're a long ways away, that potential energy is high. And then as they get closer and closer together, you get this low in the potential energy, and that's where your stable bond is. So if I pointed to this graph and said, what's this most stable bond length, you would come down here and point to this. Meanwhile, if you start getting too close together, now you get this sort of infinite potential energy. As they get closer and closer together, they can't overlap, right? You can't have the two nuclei overlapping. And then as they're really far apart, you get this zero potential energy. So that's what these sort of graphs are describing, is ideal bond lengths based on their potential energy. Okay. Now, we're going to talk about two different types of bonds in valence bond theory. The first one is sigma bonds, which we say that they're cylindrically symmetrical, or symmetrical along the bond. Now, what I mean by that is if you have a bond going sort of this way, like my arm, it would be symmetric around that, okay? Now, all of your single covalent bonds are sigma bonds. So if you see a single bond written somewhere, you can call that a sigma bond. Now, these are freely rotatable. So what I mean is if I have an atom here and an atom here and they're only bonded by a single bond, you can sort of twist the atom any way you want. They can just spin around in circles. Okay, now I'll add to this, not only is the single covalent bond going to be your sigma bond, but your first bond of any sort of double bond or triple bond. That first bond that's formed is a sigma bond. So you can think about it like when we went to draw our when we went to draw our Lewis structures, that first skeletal structure that we had that just had all the bonds attaching the atoms, every one of those are your sigma bonds, okay? Now we also have something called pi bonds, and these are going to be your second bonds and your triple bonds. So the second and third bonds that are in your systems, those are going to be your pi bonds. Now, what I mean by a nodal plane, and this will be easier once we have pictures, but sort of the preliminary before we get to the pictures, is that you have a plane that goes in between them. It's going to have two separate lobes. So the p bond will have two lobes, which, where have we seen two lobes in an orbital before? Your p orbitals, right? Your p orbitals have sort of that double balloon shape where you have two different lobes. Well, pi bonds are sort of like that too. In one pi bond, you have two lobes. Now, because of this two lobes, if you just have one pi bond, it locks it. So you can't rotate that. Now, that's if you only have one pi bond. Okay, so that would be you have a double bond, let's say. Because a double bond would have a sigma bond in it, and then it would have a pi bond in it. So that's what I mean by 1p. That should say pi. Font change on me. So a 1 pi bond atom. Now, something that has a 2 pi bond atom, and again, just put a little pi there. It changed my font on me. If you have a 2 pi bond atom, so that's a triple bond, right? So if you have between two atoms, you have a triple bond. That means the first bond there would be a sigma, and then the second and third bonds in that triple bond, those are both pi bonds. So that's going to form a cylindrically symmetrical system again. And that's a little hard to picture, and so I'll show you that in picture form here in a moment too. Okay, so now let's look at all of these. We're going to look at what a sigma bond on its own looks like and a few different ways that you can form it. We can't look at all the ways to form it right now because we don't know all the ways. And then we'll look at these systems where you have either a sigma bond and a pi bond or a sigma bond and two pi bonds. Okay, so the first one. So if we had two s orbitals and we take those two s orbitals and we combine them together, that's going to form a sigma bond. That's one way that we can form a sigma bond. Okay? So you'll notice that you have sort of a bond going in this direction, and you would get this spherically symmetrical system right here, or cylindrically symmetrical, sorry, around here. So you would form a bond. And that would just be a single bond in something like this case, where you have two overlapping s orbitals. So that would be something like hydrogen, like H2. Now, they don't have to just be s orbitals, though. You can take and you can overlap an s orbital and a p orbital, and you can also form a sigma bond. Okay? So you can combine two s orbitals, you can combine an s and a p orbital. And these little GIF animations are online too, so you can look at those whenever you feel like it. That's another way to form a sigma bond. Now, if you want to overlap two p orbitals, you can form a sigma bond or you can form a pi bond. It all depends on how you overlap them. So looking at the shape here and the shape here, do you think when we want to make a sigma bond with two different p orbitals, should we overlap them sort of end on end or sort of side on side, which would give us the same shape or similar shape? Yeah, end on end. So you can take the two p orbitals and you can overlap them like that. And that will also form a sigma bond. Okay? Now, in a few moments, we're going to get into something called hybrid orbitals. And you can make sigma bonds with all your hybrid orbitals as well. You just have to overlap them in the same way. You have to overlap them end on end. Okay, so those are sort of your three different ways to form sigma bonds. All right, you can form them with s orbitals. You can form them overlapping with an s orbital and a p orbital, or an s orbital and a hybrid orbital when we get to those, or with two p orbitals, end on end. If you twist these sideways and try to go kind of side on side, that's a different bond. Okay, so let's look at this slide one more time and go over this one more time. So cylindrically symmetrical, that's just describing that shape, right? Think of a cylinder. What does the cylinder look like? Okay, that's cylindrically symmetrical. So that's what we mean by the symmetrical part. They're all your single covalent bonds, so we talked about that before. If you have a single bond or the first bond in any of your double and triple bonds, those are sigma bonds. And they're freely rotatable. So you can see on these how there shouldn't be any reason that this can't rotate, right? There shouldn't be anything that stops that from rotating. And so it can rotate along those bonds. Okay, now let's move on to the next one then. So now we have pi bonds. Now, I have sort of a large atom here drawn out that we don't know everything about at the moment, but this is the easiest way to point out what a pi bond looks like. So, at each, in here, and then sort of behind that where you can't see, those are all going to be carbon atoms. We don't know what all these green and blue orbitals are quite yet. You can think of them as a combination of S and P orbitals for right now until we get into that in more detail. This would be a hydrogen, that yellow one would be a hydrogen, and that would be a hydrogen. So what would we call this bond right here between what I'm calling a hybrid orbital that we'll talk about in a moment and the hydrogen S? Sigma bond, right? It's a single bond. Everything on here is single bonds except one thing, and that's this bright pink. That's going to be your pi bond, okay? So notice there's two lobes to it, but that's still just one pi bond. So this bond right here, that would be your single bond, and that would be a sigma bond, all right? And then this two-lobed system right here, that's the pi bond. Now, I talked about the other ones being being rotatable, right? Look at this one with this double bond system here, where you have this single bond and then the p bond or the pi bond making your double bond. Does that look like you could just rotate it, or would it kind of get stuck? It would get stuck, right? So that's why if you have a single, or if you have a double bond, you can't rotate that. Double bonds won't rotate. Okay. So sort of pointing everything out to you, and we'll go over what all these orbitals are in a minute. Any of your single bonds are sigma bonds. If you have a double bond, you have both a sigma bond and a pi bond, okay? The first one would be your sigma bond. It makes your connectivity, and then you would have your pi bond. Okay, so then we have one more thing to go over, and that's if we have a system where we have a triple bond. If we have a triple bond, something like C2H2, what happens is we get one sigma bond, and you can't see the sigma bond, it's hidden, and then we get two pi bonds, all right? Now, if we have that two pi bonds, what happens is they actually sort of combine together, and they make this cylindrically symmetrical system right here, all right? So these are the different ways that you can get pi bonds. You can get a double bond, where you have your single bond here, your sigma bond, and then this forms your second bond, your pi bond. And this can't be rotated. Or you can have this system where you get two pi bonds and one sigma bond. So one of these is a sigma bond, two of them are pi bonds. And then you get this sort of spherically symmetrical system going again. Okay. So that sort of talks about the different kinds of bonds and gives you some basis to talk about bonding. And I can, point to any sort of large molecule, like for instance, look at your worksheet this week in discussion. If you look at all of those aspirin and things of that sort, and you look through it, I can point to any of those and say, how many sigma bonds are there? How many pi bonds are there? And what you would do to figure that out is you would go through, and every time you see a bond, or a single bond, that's a sigma bond. If you see a double bond, one of those is a sigma bond, one of those is a pi bond. If you saw a triple bond, one would be a sigma bond, and then two of them would be pi bonds, okay? So that's one of the ways that I tend to ask these sorts of questions a lot, to make sure you know which ones are sigma and which ones are pi. Okay, yeah. Yes, this one can be rotated. This one right here can't be, but this one is able to. Okay? All right. Now let's talk about something called atomic orbital hybridization. So this gets into this idea of you have MO theory and you have hybridization theory. So the first one to talk about is hybridization theory. The great thing about this one is that it's very, I'll say simple here, but it'll be simple once you learn it, sort of thing. It's simple once you know it. And then we have MO theory, which is more complicated. So atomic orbital hybridization theory gets into this sort of thing that we can do with really big molecules. I can ask you questions on, all of those drugs that are in your worksheet this week. And I can point to any sort of molecule or any sort of atom in a really large molecule and ask you about the hybridization of it. And it doesn't matter how big the molecule is, you just look at that one atom and tell me about it. So in this system, what you're doing is you're taking your s and p and d orbitals, you're combining them together, and you're making all new orbitals out of it. Now, what these orbitals are going to be called is sp, sp2, sp3, and when we get there, sp3d, and sp3d2, okay? So it's sort of taking all of these atomic orbitals, combining them together, making them look a little bit different now because they're a combination of the other, and then using those to bond with. So we're gonna go through this really fast on this slide, and then we're gonna break it down. This is sort of an overview slide. So we have something called sp orbitals. And those sp orbitals, they're gonna be made if you take an s orbital and you take a p orbital and you combine them together. Right? So sort of not too bad nomenclature. So you take an s orbital, a p orbital, you mix them together, and now you get two new orbitals, and what they're called sp orbitals. So sp2 orbitals, then you take one s orbital and you take two p orbitals, you mix them all together, and you make three new orbitals, and those three new orbitals are called sp2 orbitals. Anyone want to guess what sp3 orbitals are made out of? Good. An s and three p orbitals. Pattern recognition, it's important, right? Okay, so you take an s orbital, you take three p orbitals, you mix them together, and you're going to get four new orbitals now. We take four orbitals, we make four orbitals, and we're going to call those orbitals sp3 orbitals. Now, those new orbitals that we've made, that's what we're going to use to make our single bonds with, or our first bonds, and that's what gives us our Vesper geometry, okay? So once we get these all made, you'll see that's where our geometry kind of comes from. Okay, so now let's take each of these cases along with the sp3d cases when we get there and look at them in a little bit more detail. Oh, and any p orbitals that were there before and you didn't use, they're still there. So for instance, right here, if we have an s and a p orbital, what's left over? Two more p orbitals. Those are still around, and we can use those for things. Okay. So in more detail now. Actually, I'll go back a sec. It looks like everyone's still writing. I'll give you a few more seconds. Okay, so now we're going to take each of these cases, we're going to break them down into basically a slide for each one of these, and we're going to look at how it works. Okay, so let's just draw an energy level diagram, right? Same sorts of things we've been drawing that I made you draw in the last midterm. So it doesn't matter what level it is one of the levels. So we have an s orbital and we have three p orbitals, okay? Now, if we want to make an sp hybridized system, what we're going to do is we're going to take this orbital, and we're going to take this orbital, and we're going to mix them together. Okay? We're going to combine them. If we take those orbitals and we make new orbitals out of them, do they exist anymore? No, we destroyed them and we made new orbitals. So we're going to take those orbitals and we're going to make new ones. Now, of course, my numbers aren't exact here, but do notice, is this a little bit higher than this, you think? Yeah. It's an average in energy, okay? So the sp orbitals are going to be a little bit higher in energy than s. They're going to be lower in energy than p. They're going to be an average between the two. We've taken these orbitals and we've made new orbitals out of them, so they're gone. We can't use them anymore. We've made these new orbitals. Have we touched these p orbitals at all? No, so they're still around, okay? They're still there. Now, if I point to this orbital and I say, what's the name of that orbital? What are you going to say? An s orbital. And I point to this orbital. What's the name of this one? P. And I point to this and you say, and I point to this and you say, sp. Good. Yeah?
How did you get two orbitals out of only one s and one p?
Okay, good question. So every time that you combine these orbitals, the number of orbitals that you start with is how many orbitals you get out. Okay? So that's actually really important. If you combine an s orbital and a p orbital together, you're going to make two new orbitals out of them. You're sort of averaging them out and you're making two whole new orbitals. And when we get to sp2 orbitals, you're going to combine an s orbital and two p orbitals. So how many sp2 orbitals will you have? 3. So no matter what, and this is going to hold for MO theory too. No matter how many orbitals you start with, you end up with that exact same number of orbitals, okay? You're making new orbitals out of them. It's maybe combining isn't the best word. That makes it sound like you're turning them into one. But you're always going to come up with the same number of orbitals that you started with. Okay. So, speaking of, you combine two orbitals, you get two orbitals. When we combine three orbitals, we'll get three orbitals. No matter how many orbitals you combine, you get that same number back. If you combine an s and a p, you get sp orbitals. That is the name of the orbital, just like this, the name of this orbital was s and the name of this orbital was p. Okay? So when we start doing things with this, particularly making bonds, and I ask you what sort of orbitals are involved in the bond, you would call this an sp orbital, just like you called this an s orbital. Okay? Now, the energy of this sp orbital, it's going to be between that of an s and a p orbital. So if we were drawing this to, some version of scale, you would want to draw that sp orbital a little bit higher. You're sort of averaging them. Okay. Now let's see what these things look like. So this is what an s orbital looks like. This is what your p orbital looks like, right? So an sp orbital is going to look sort of in between the two. So you're going to have two sp orbitals and then two leftover p orbitals. So this is what your new system looks like. And it's a little bit hard to see what those orbitals actually look like, so I'm going to expand them out. So these are what your sp orbital looks like. Kind of an in-between. They're not quite an s orbital, they're not quite a p orbital. And so they look like this. Now, when you draw them all combined, you can't really see it that well because these little second pieces are hidden. So that's why I have them expanded out for you. Okay? But notice your p orbital is still there. That green p orbital is still there. And now you've just taken this p orbital and that s orbital and made these two new orbitals out of them. Okay? All right. Next one. Oh, and then one more thing. Notice that if you were to make a bond with this one and a bond with this one, that would be a linear molecule, right? Okay. We'll go into the VSEPR part of it in a little bit more detail here in a minute. Okay, now let's do the exact same thing for sp2 orbitals. So we have our energy level diagram. Now we're going to take one of these, and we're going to take two of these, and we're going to combine them together, and we're going to get three new orbitals. And we have this. So these orbitals have now been remade into the sp2 orbitals. Have we touched this orbital? No. So is it still there? Yeah, that one's left there. So when we do sp2 hybridization, we get three new hybrid orbitals, and we get a leftover p orbital. What is the name of this orbital? Okay, let's do this again. What's the name of this orbital? The name of this orbital? The name of this orbital? Good. Okay, so again, we're combining three orbitals, so we're getting how many new orbitals? 3. We're taking an s orbital and a p orbital and we're mixing them together, and so we get sp2 because it's one s and two p's combined together. sp2 is the name of the orbital, just like s and p was over here. This was s, this was p. Now the name of this is sp2. Yeah? Great question. So what do we think? Is sp2 going to have a higher energy than an sp orbital? Yeah, so good. Because you're taking now and you're combining two higher level energy orbitals with this lower level energy orbital. And so on average, if you're talking same energy, shells and everything like that, the sp2 are going to be a little bit higher in energy. Do we think they're going to look more like a p orbital or less like a p orbital than the sp orbitals? More like a p orbital. Okay, and you guys are kind of psychic on the questions today. I like it. So energy of an sp2 orbital is between that of an s and a p orbital, and it's also higher than an sp orbital. Now let's look at what these look like. So now we're taking our s orbital and our 3p orbitals and we're combining them together or mixing them together and making new orbitals with them. And so what are they going to look like? So this will be the basic system that they look like, okay? Now, again, because it's sort of tough to see this all combined, I did take the sp orbitals and sort of move them out. So you'll notice these are a little bit more p orbital-like than s orbital-like. We still have this sort of double lobe system, but they're a little bit more like a p. And now we're getting a little bit different geometry too, right? Now we have this sort of geometry where they're one this direction, one that direction, and one that direction. So we get a trigonal planar geometry. Okay, last one for right this second. Okay, now we have sp3 orbitals. So we're going to do the same thing. So if we take our s orbital and all three of our p orbitals, how many p orbitals will we have left over? None. What orbitals will we have? What are the name of them? sp3 orbitals, right? So it's sp3 hybridization and we get sp3 orbitals. How many of them will we have? Good. We get 4 of them. Now, things to notice. Same idea as last time. We started with 4 orbitals, we mixed them together, we got 4 new orbitals. We combined an s and then 3 p's, so the nomenclature there is sp3 orbitals. So it's sp3 hybridized and we have sp3 orbitals. And then the energy of this, it's higher than the sp, it's higher than the s, it's higher than the sp's, it's higher than the sp2s, but it's still going to be lower than the p's would have been. All right. Now, these will again look a little bit more like a p orbital than before. So when we combine all these together, what geometry do you think we're going to get? So we've had linear, we've had trigonal planar, and now we have 4 things. Tetrahedral, good. Now these actually get really like messy to draw, so I just drew 1 lobe of each. It's pretty standard to draw it like this because it gets really hard to see otherwise. So when you look at how they're bonding, they would form 1 bond to each of these, and you would get a tetrahedral geometry from it. Okay. So I think you have the pattern down now. So for the D hybridization, we're going to go a little bit quicker and without quite all the drawings done out. Okay. So now we have these 2 other hybridizations, sp3d. So what do you think you combine to get sp3d? And how many s's? How many p's? How many d's? Okay, what about sp3d2? How many d's? And of course still that s and the 3 p's. So if we have sp3d hybridization, so right here, how many orbitals would we have? How many hybrid orbitals? 5, right? We combined an s, 3 p's, and a d. So we started with 5 orbitals, we mixed them together, we got new orbitals, we have 5 orbitals. So if we have these, we get a trigonal bipyramidal. Okay? Now, what about sp3d2? How many orbitals did we start with? 6. How many hybrid orbitals would we have? 6. What would the name of those be? sp3d2, right? Same idea as before. The hybridization type is the name of the new orbitals. And then if we have 6 orbitals and we have to spread those out as far apart as possible, what geometry would that be? Octahedral, right? Each one forms, your hybrid orbitals are always going to form your sigma bonds. They're going to form your single bonds. Okay. So that's sort of how hybridization works. That's kind of the theory behind it. Now, how do we figure out the hybridization of something? If I give you a structure and I say find the hybridization of something, or worse yet, I give you just the name and I say find the hybridization, the first step you have to do is draw the Lewis structure, okay? Sort of the first step to everything so far in this since the midterm. So you're going to draw out the Lewis structure. This gives you the arrangements of the electron pairs and the bonds, right? So we'll know how many bonds and how many electron pairs you have. you take and you determine your steric number. So remember what that was, right? We did that when we did VSEPR geometry, and we figured out, well, the number of atoms that are bonded to it. Now remember, that wasn't number of bonds, right? This was the number of things that were bonded to it. So double bond then in that case would count as 1 or 2? Just 1, right? It's just 1 atom bonded to it, plus the electron pairs. Now that's the number of hybrid orbitals that you need, okay? So once you find that steric number, that's your number of hybrid orbitals that you need. Now, if you need 2 hybrid orbitals, what sort of how many orbitals, so we need 2 hybrid orbitals. How many orbitals do we need to start with to get 2 orbitals? 2, good. However many orbitals we need is how many we have to start with. So we need 2 orbitals, so we start with 2 orbitals. What hybridization has 2 orbitals to start with? sp, right? Now let's say we do this, and we do this, and we do this, and we need 3 hybrid orbitals. What would we have to do for hybridization? sp2, right? 1s and 2 p's. If we need 3 orbitals, we start with 3 orbitals. So we start low and we work our way up, s, 2 p's. If we need 5 orbitals, well, start low, work high. So we have an s, 3 p's, and a d. So we would need sp3d hybridized. All right? So that's sort of the pattern for how you figure out what hybridization you're going to have an atom be. First, you draw the Lewis structure, then you can find the steric number. Once you find the steric number, you can go and you can say, well, that's how many hybrid orbitals I need. However many hybrid orbitals I need is how many orbitals I need to start with, and then you count your way up to the right number of orbitals. So this should be in your notes. This comes from the other book again, so the Chang book. So, but I like this sort of chart for you. So I included that in there for you so you have it. So this goes through and says, well, how many atomic orbitals did we start with? It's sort of the summary for all of what we just talked about. What's the hybridization? What is the number of hybrid orbitals? And then the geometries, okay? I don't suggest you memorizing this table. I suggest you using this as sort of a summary to make sure you know what you're doing. The easiest way to do the hybridization is to go through how we just did it on this slide. And to sit and say, well, if we can figure out our steric number, then we can figure out how many hybrid orbitals we need. And we can count the number of orbitals we need to start with. Memorizing this is sort of not as useful. Okay, let's relate this back to the worksheet that we did with VSEPR geometry. You may want to pull it out if you have it handy. This is one of those, you know, the Lewis structures and then this worksheet are really useful to just kind of keep around you all the time. Okay, so if we have a steric number of 2, I'll give you just a sec. Okay, so if we have a steric number 2, how many hybrid orbitals do we need? 2. Whatever your steric number is, that's how many orbitals you need. So if we need 2 orbitals, how many orbitals do we start with? 2. So what orbitals are we starting with? An s and a p. So what kind of hybridization is that? sp. Okay. Steric number 3. How many hybrid orbitals do we need? 3. So how many orbitals do we need to start with? 3. So we're going to have sp2. Good. All right. Now notice it doesn't matter how many lone pairs you have. All that matters is your steric number. Okay. So steric number 4. If we have a steric number 4, how many hybrid orbitals do we need? 4. So how many orbitals do we need to start with to get that? 4. So we're going to have an sp3. And that's for the whole, whole steric number 4. All right? So we figure out our steric number. That's how many hybrid orbitals we need. That's how many orbitals we have to start with. I'll go back a sec. I have like 4 people taking pictures and I just, clicked it right when they were all going. Okay. So, steric number 5. And for people taking pictures, this is the no animations on this one, so you can take it whenever. So, we have a steric number 5. How many orbitals do we need? How many hybrid orbitals? 5. So how many do we have to start with? How many do we need? 5, so we start with 5. Good. So we have sp3d. All right, and then the last one. We have a steric number 6. So how many orbitals do we need? How many do we need to start with? So we have sp3d2. All right? Okay, so that's how the whole hybridization idea works, and kind of the fast way to solve it. Now I want to go back to this picture for just a moment, because now it's a little bit easier to see what's going on, because you know what the hybrid orbitals look like. So I said that here, here, and here were carbons. So we basically have a C3 system set up. Now, this right here, these are your hybrid orbitals bonding to your hydrogens. How many of these do you have? 4. So what kind of hybridization is that? Yeah, sp3, right? 4 orbitals, so we start with 4 orbitals, so sp3. All right, now this one. So the green for each one of these would be your hybrid orbitals. So how many orbitals do you have right here? It's a little tough to see, but 1, 2, 3, right? So what hybridization does that carbon have? Good, sp2. And then it had a leftover orbital. If it's sp2, what's left over? A p orbital. Where do you think that p orbital is? It's right here, right? So this p orbital that's left over, what bond is that making? Your pi bond, okay? So it uses all of its hybrid orbitals to bond with this carbon. You can't see it too well, but there's a hydrogen in the back. And then it bonds with this carbon. So its hybrid orbitals are all used to form what kind of bonds? Sigma or pi? Sigma bonds, okay? Hybrid orbitals are used to form sigma bonds. And then the leftover p orbitals, those are forming your pi bonds. Okay. Now we'll look at this again in a slightly different way. So double or triple bonds on hybridization. Okay, so we have C2H4. So if we draw the Lewis structure, it looks like that. Now, as you're studying for this, it's a good idea when you look at slides like this to perhaps, only start with the C2H4 and try to draw this on your own. So each carbon is going to have 3 atoms bonded to it, right? You have a bonded H, a bonded H, and a bonded carbon. So what kind of hybridization is it going to have? sp2. So yes, you would have written it right, but its terminology is sp2. Okay, so now what do you think is forming this bond, and then this bond, and then that first bond to the carbon? Which orbitals? The sp2 orbitals, okay? Your hybrid orbitals form the sigma bonds, which are to the hydrogen and the hydrogen, and then one of these. One of these is a sigma, and one of them is a pi. Good. Okay, so this is the sort of drawing of just the sigma bonds, okay? This is your sigma bond only drawing. So if I were to point to this bond right here, keeping in mind this is what it looks like, and I said, what orbitals form that bond? Okay, sp2, would you get all the points for that? If I just said what orbitals form that bond? What other orbital is forming that bond? We can't forget about the hydrogen, right? So if I said what bond, or what does the carbon use to bond with, what would you say? sp2. If I said what orbital, or what orbitals form this bond, what would you say? sp2 and the s orbital from the hydrogen. Okay? What about this one? Same thing, right? The carbon uses the sp2 orbital and the hydrogen uses the 1s orbital. Now, what about this sigma bond between the 2 carbons? What are those being formed by? An sp2 orbital from this carbon and an sp2 orbital from that carbon, okay? So you have 2 different sp orbitals overlapping. Notice they overlap end on end, right? That's what forms the sigma bond shape. Okay, now we've talked about all of the sigma bonds. What about the second bond here? What's that called? Pi bond. What do you think forms that bond? Yeah, the leftover p. That's the only thing we have left, right? We've used up all our other orbitals. Do we have an s orbital left on this carbon? No, there's no s orbital. We took it away and we made it into an sp2 orbital. So we take that leftover p orbital and we use that to form the double bond. Now this is then sort of what it looks like. So notice this is the same picture as before, and you can sort of see this in here, right? You want to look at that here and that here. That's the hydrogen and the hydrogen. So you get this sigma bond, sigma bond, sigma bond, sigma bond. And then the p orbitals come up. And remember, how many lobes does a p orbital have? 2. And so if you overlap them sort of perpendicular to each other, your pi bond is also going to have 2 lobes. Okay. So if I make this molecule, or I tell you to make this molecule, one of the two, and I say, how many sigma bonds are in it? Take a second. What would you say? All right, how many sigma bonds? 5, right? 1, 2, 3, 4, and then one of those is 5. How many pi bonds? 1. Good. It'd be one of these. Okay? Just be really careful. It's 1 pi bond. This is not 2 pi bonds, it's 1 pi bond. We have a sigma bond here and then 1 pi bond with 2 lobes. All right. So let's go through some questions. Oh, wait, no question? All right. Let's go through some questions a sec. Okay. What orbital does hydrogen use to bond with? Good, 1s. What orbitals does a carbon use to bond to the hydrogen with? Good, sp2. Not s, not s and p, not p. It bonds with the sp2 orbital. Now, what does carbon use to bond with the carbon in the sigma bond? Good, sp2. It uses that hybrid orbital. We made the hybrid orbitals based on how many things was bonded to it, and then lone pairs as well. Not that we have to deal with it here. So that's what we're going to use to bond. Now, what does carbon use to bond with the carbon in the pi bond? P orbital. Good. So this is a perfect example of how I like to ask these sorts of questions. Yeah? So it's not so much that it's actually not coming from anywhere, it's just left over. So we start with 1s and how many p's? 3. And then how many did we use up? We took away the s orbital and we took away 2 of the p orbitals. So how many is left over? Just 1, right? So we use that leftover p orbital as our pi bond. Okay, so that's...
So say if it was H and S, like say if it was H2, would the orbital used to bond those would just be S?
You mean just like H and H, just H2, simple as H2? Yeah, it would just be 1s and 1s bonded together, no hybrid orbitals there.
But so because it's bonding to the carbon first and then the hydrogen, that's an sp squared?
So careful, we're talking about individual atoms here. So in this whole section, the hybridization, this switches when we do MO theory, but for this whole section, we're all talking about individual atoms. So this carbon uses the sp2 orbital. The hydrogen, though, still uses the s orbital. So the better picture of that is actually on this slide. So the hydrogen is still using the s orbital to bond, so that didn't change. So just like if we had 2 hydrogens bonded together, this is still using the 1s. It's the carbon then that is using the sp2. Anything else? Okay. All right, so then our next sort of example here, we've done the single bonds and the double bonds. Now let's do the triple bonds. So first of all, let's look at the hybridization. So if we take this carbon and we bind it first to this carbon and then the hydrogen, what's our steric number here? How many things are bonded to it? 2. And how many lone pairs? None. So 2 things bonded, no lone pairs, so our steric number is 2. So how many orbitals do we need? How many hybrid orbitals do we need, I should say? 2. So how many do we have to start with? 2. So what is our hybridization? S and a P. So SP. Okay. Now, what do we have left? If we've taken away an S and we've taken away a P and we've made these SP orbitals, what is left over? 2 P orbitals are left over on each carbon. Remember, we're talking about, because they're the same, we're talking about them in a similar way, but on each carbon. Okay. So those 2 P orbitals are going to make your pi bonds. So your first hybrid orbital, or excuse me, one of your hybrid orbitals is going to be used to make your hydrogen bond, or your bond with your hydrogen, I should say. And then the other hybrid orbital is going to be used to bond with the carbon. And then the 2 leftover P orbitals are going to form these pi bonds, each one with 2 lobes to begin with. But what ends up happening here is you actually end up forming this sort of cloud system where it combines into one. Okay? All right. I will let you do this a sec before we move over to the document scanner. Okay, so now we're going to do some, oh yeah. Yeah, you mean what the P orbitals are coming from? Okay, so let's go back to a picture here again. This is worth spending an extra few minutes on. Okay, so let's go back to like these slides, this area of the slides for a second. So if we're taking, for instance, let's say sp2, and we're combining these orbitals together, we get how many orbitals left over, or back? We get 3. Now, did we touch this p orbital at all? No. So what happens to it? Well, it's just there, right? We can do things with it. That stays. Now, same thing with sp hybridization, which is the example we've just done. You take an s and a p orbital, and you combine them together. And how many p's do we have left over? 2. So do they go anywhere? No, they're still just around hanging out waiting for us to do something with them. So we can use those to bond. So in these systems where we have leftover p orbitals, you can be a little bit quiet while you pack up. This question has been asked multiple times, so I know a lot of you are still confused about it. So we have these 2 leftover p orbitals. And so these orbitals are going to be used to do what? Sigma bonds or pi bonds? Sigma bonds, or lone pairs, which we haven't had an example with yet, or lone pairs. And then what are we going to do with these leftover orbitals? Our pi bonds.